In the previous video I demonstrated a gesture module, and also I constructed a CI5 interface that's to go between the gesture module and my ICOM 706. In this video I'm just going to briefly go over the software which I mentioned in the previous video. Here is my sketch on the IDE on the computer. As with all sketches, it's got some libraries that have to be included, in this case the keypad and the liquid crystal, and then the variables and constants, and eventually we come down to the thing called the loop. The loop does most of the work. In my program I have a number of functions that the loop calls. Here it is here, single frequency, frequency tune, scan start, and so on. So the loop goes to each of these functions, goes and finds out what it needs to do, and then comes back. And it just keeps going round and round the loop until it finds something to do. In order to keep the video brief, I'm just going to concentrate on a couple of items. One is how do you send a single frequency from the Arduino to the radio, and how do you enter other frequencies such as those derived from a keypad. So I'll concentrate on those two items. The IC 706 uses the CI5 bus system to communicate between the controller and itself. In the manual for the IC 706 there's some information as to how you arrange the CI5 data. I'll just go down, for example, on this one here, which details what you have to send between the controller to the IC 706. It starts off with a couple of 8-bit bytes with hexadecimal values in them, FE, this is the wake-up call, 0x48 or hex 48, which is the address of the 706, the address of the controller. Now E0 is a default for all controllers, then a command number, and then a sub-command number, and then some data if you're sending frequency information, and finally end of message. So very briefly, here's an example of the command table. Command number, for example 06, followed by 00 means let's go to lower sideband, or 06 followed by a 01, let's go to upper sideband. In the frequency control section, if you send a 05 then followed by a string of what I call binary coded decimal numbers, it'll send the radio to whatever frequency you've told it to do. So how do we send the information to the IC 706? Well, here I've called what's called the USB mode function. The loop comes to this spot. It checks to see if the button, the USB mode button, has been activated by using the word digital read, and then it starts to send a series of write commands via the serial 1 connection. The Mega has 4 hardware serial ports. I'm using serial 1. So it runs through these codes, sends these codes. This is the start codes. The address of the radio, which I've already defined as 0x48 back at the start of the program, the address of my controller, and the code words for upper sideband, which I also defined at the start, and then finally OXFD, which says end of message. I also write to the LCD screen with some information to tell me that I've actually selected upper sideband mode on row 1. So here in my notes I've made a little drawing which shows the sequence required to send a frequency to the 706. In this case I'm going to send 144 megahertz, 123.456. It's 9 digits. I'm only going to send 8 digits because I'm going to ignore the hertz component. The IC 706 requires you to send the hertz digits first, followed over here, followed by the next numbers up, all the way up to the meg. So the first things that get sent are 5 and a 6, a 3 and a 4. The 5 and 6 represents the 56 down here of the tens of hertz and hertz, all the way up to 1 of the 144 megs. But there's also a 0 there because we need to make up 5 full bytes, not 4.5. Each of these bytes contains a number which is in binary coded decimal. None of the numbers go over 9. That makes it a little bit easier. As you can see, just simply take your frequencies components and put them in these little boxes and send them off. So here's the command for sending frequencies to the radio. Again, the preamble bytes, and then the actual variables that represent the hertz, kilohertz, hertz, and so on. You'll see there are 5 bytes there. and they're sent as BCD digits, and end of message. So that's just how it's all constructed, how the stream is constructed. Hertz, finally megahertz. When the program starts, I actually send 7.1500 meg to the radio just as a default frequency, and here you can see hertz equals 00. You've got to use byte 00 for zeros. Then kilohertz hertz, which is the next two zeros, and then kilohertz, which is 15. That's OX15, and then 7 megs, which is actually 07. You have to include the 0, because it's got to be an 8-bit byte, and as I mentioned, each digit only occupies 4 bits of an 8-bit byte. Sending a frequency via the keypad is a little bit more complex. The library called keypad does all the work for you. You push a button on the keypad library finds out what button you've pushed and assigns it to a position in an array. I've defined an array here called my key. The array is, my array is 16 bits wide, but I'm only using 8 bits of that array at the moment. As each key is pushed, the character that represents that button is stored in the first, second, third and fourth position of the array. There is a little loop counter here using a variable k. K is incremented by 1 and steps each of the entries through the array until we get to 8. When we get to 8, it goes back to 1. Now the characters in the array are ASCII characters. In order to find the numbers, you need to subtract 48, which then puts the result into the numeral part of the ASCII table. In addition to filling the array with the numbers as I enter them, that is from the megahertz to hertz, I also print the contents of the array on the LCD screen. So just to show you that on the actual unit here, I'll enter 144 megahertz. 1, 4, 4, 1, 2, 3, 4, 5. I only go to 8 digits. If I enter another more digit, it'll go back to that position. So we don't want to do that. When I'm finished with that, I'll send it to the radio, and there it is up there. So that's how the LCD displays each digit as I enter it. So having filled the array with 8 digits, I've now got to send it to the radio. And what I do, I take the contents of the array and I give it a variable name, such as in digit 0, etc. That way I don't muck up the contents of the array. That'll stay the way it is. Now in order to send it to the radio, what I've got to do is actually send the last bits first. So I muck around here with some equations. The first set of equations gives me a long number, which is the actual frequency, and I put that on the LCD display. The next part of the system takes 2 digits, for example the 2 hertz digits, and forms one 8-bit byte. I need 2 digits to fill an 8-bit byte. Not only that, but I also need to make sure that the digits are in binary coded decimal. In order to do that, there is an equation here where you take the value of the digit divided by 10 multiplied by 16 and then take the modulus. That will convert the number into a binary coded decimal number. Converting the digits into a binary coded decimal format is a little bit of fun actually. We take the number, for example 45, which is part of the frequency of our 144 meg example. We divide it by 10 and we end up with 4.5. Now it has to be an integer, so we get rid of the 0.5 and we end up with a 4. We then multiply that by 16 and we end up with the number 64. So the next part of that equation is we take the modulus of 45 to the base 10, which really means is divide it by 10 and take the remainder. In this case the remainder is a 5, so the modulus is 5. So we have two numbers, 64 and 5. Together they add up to 69. So what do we do with that? Now as far as the radio is concerned, it wants an 8-bit byte, and the 8-bit byte is broken into 2 halves, 4 bits here and 4 bits there. One of the digits goes here and one of the digits goes there. The radio just wants 1s and 0s, it doesn't want numbers. So we take the 69 and we're going to prove that it actually equals 45 as far as the radio is concerned. And the way that works is 69 consists of 64 plus 4 plus 1. You'll notice these are binary weights. 64 on an 8-bit byte is in that block there. That's actually a wire number 2. 4 is way down here and 1 is way down here. Now if you have a close look, if you just take a 4-bit chunk of the byte, that actually is 4 because it's in that position as in that one there. So we have 4. The 5 is a 1 here and a 1 there, which adds up to 5. That adds up to 45, which is what the radio sees. It doesn't see 69, it sees 45. Something I need to mention, we need 2 digits per byte. One of the digits will be tens and one of the digits will be units. So for example, if I push the button 4 of the 45, the 4 really means 40. So what we do is we take that particular digit and we multiply it by M1, which happens to be 10. And we take the next digit and we multiply it by 1, which happens to be 1 or no 0 or just 1, just the numeral 1. So that's how we form a 2-digit number with units and tens. These are given the variables F key 1 up to F key 5. We need 5 bytes, even though one of them looks like it's only half a byte. We actually will add a 0 in that position. You can't send half a byte. You have to send the full byte, but we're only interested in 8 numbers. So once we've made our 2-digit numbers, which are these variables here, we then equate the hertz, kilohertz, etc. to those 2-digit numbers, and then we go to our little part of the program which sends all that information off to the radio. Just to go back, that's the one that says, the function says send to radio. The preamble and then the components of hertz, kilohertz, hertz, etc. 5 8-bit bytes, and then the end. So the radio then goes to that new frequency. So here is the data stream that goes from the microprocessor to the radio. The preamble, address of the radio, address of the controller, the control number for frequency, and then the data. Now you'll notice that the byte that gets sent first is the 5 of the hertz, tens of hertz. The 6 is not sent. I send that as a 0. I only send 8 digits, not 10. Then the 34, the 12, the 45 in that order, and then the 100 megahertz is 1. Hundreds of the next digit up, thousands of megs, is sent as 0. So that's the 5 bytes. You can't send half a byte, so you've got to put a 0 there and a 0 there. So that's the stream. My program also contains the ability to step in 10 Hz, 100 Hz, 1 kilohertz and 100 kilohertz steps. I got a little program here which does it by counting from 1 to 99. As I count from 1 to 99, I convert the decimal value of the count into a BCD number and send it straight off to the radio. When it gets to 99, for example the hundreds of hertz, I then jump into the next section, which then pulls me into the kilohertz section. So I've got a loop within a loop, and that's how we go up in frequency and go down in frequency. We count backwards, we go count -1. So that's a very brief look at how we go around stepping around the frequency that we've sent. The radio can send information back, but not much. My IC 706 doesn't send much back. Most of the stuff has to be done by the processor telling the radio what to do, but it will send back information if the code's incorrect. I only use that during the debug process. It will also send back the frequency as you dial it, but you have to rotate the dial for it to send back to my Arduino. Later versions of the ICOMs do have a code which allows it to read the actual dial frequency without having to do that. But I only use the replies during the debug because it does slow the system down, and you can tell what's going on by looking at the screen of the radio, so you really don't need to know. You'll know if it didn't work, nothing happens. During the debug process, I can also use the IDE's serial monitor, and I can just check each of the variables as they happen to see if something goes wrong. I don't run that all the time. I only run that when I need to see what's going on. So these are the commands: serial print to, let's say, F1, and you can see it come up on a separate little screen on the actual computer. That's when the computer is connected to the Arduino.